So calculating pH or doing calculations with weak acids and bases is more complicated than doing it with strong acids and bases. And really what it's going to come down to is being able to do ice calculations like you did for the equilibrium topic. Because the key difference is that while a strong acid or a strong base fully dissociates into ions, with weak acids and bases, they are considered to not be fully dissociated, so they are at equilibrium. And so what you really need is you need to be given an equilibrium constant for a weak acid or base that tells you how much does it actually dissociate, what percentage of the acid or base molecules actually split apart into ions, into H plus ions or OH minus ions. So here's a classic weak acid example, ethanoic acid, CH3COOH, reacting with water, dissociating apart into its conjugate base, the ethanoate ion, and H3O+. And so if I just tell you that it has a concentration of 0.1 mole per dm cubed, you don't know what the pH is because you don't know how much does it do this, how much does it split apart. So here's what we do. We can set up an equilibrium constant expression, products on top and reactant concentrations on the bottom. Since water is so prevalent in these solutions, and there's so much more water present than anything else in these solutions, we can assume that its concentration is essentially constant. And so whenever we have liquid water in one of these equilibria, we don't actually include it in the equilibrium expression for our acids and our bases because it is essentially a constant value. So you notice I pulled it out of the expression to the other side of the equation. And now what I'm going to call this, instead of just calling it a generic Kc, I'm going to call it Ka because it refers to how much an acid is dissociating. So this is like a equilibrium constant for an acid. So we removed the water, but otherwise it's the same as an equilibrium constant expression. And now we call it Ka. Okay, so that will always have H plus on top along with the conjugate base, and it will have the acid molecule on the bottom. So Ka is known as the acid dissociation constant. And it works the same way as an equilibrium constant. The bigger Ka is, that implies more products on the top, which implies more dissociation. So that's a key idea. With bigger Ka values, it means more products, and that means more dissociation. So that all would mean like a stronger acid. So the higher the Ka value, the stronger the acid. And it just has to do with the idea of equilibrium and interpreting the value of an equilibrium constant. For a base, you're going to get the exact same type of expression, only we call it the Kb. It's the base dissociation constant. Again, we pull out the water from the expression, and so you get the ions on the top, with OH minus being the important ion now, and you get the base molecule on the bottom. And it works the same for Kb's. The bigger the Kb value, that implies more dissociation and a stronger base. Now, when you look in the table of weak acids and bases, which is here, table 21 or section 21, I've highlighted a few key parts. You notice that they don't actually give you a Ka value and they don't actually give you a Kb value. They give you a pKa and a pKb. Now, for the same reason that pH gets used, which is that it makes it easier to compare values and you get to avoid using big, clunky exponential terms. For the same reason, we're going to use pKa's and pKb's when we refer to weak acid and weak base strength. So, for example, here's why it's useful. Ka of ethanoic acid is 1.78 times 10 to the minus 5. These weak acids and weak bases they dissociate to such a tiny degree that most of the time their values, their equilibrium constants, the Ka's and Kb's, are these tiny decimal numbers, right? This is 0.0000178. Or 1.78 times 10 to the minus 5. That's a very small number, and it's kind of a big, clunky number with scientific notation. So rather than presenting it like that, which is valid, that's the Ka value, if you do the same thing, anytime you see P in this topic, it means we're taking negative log base 10. And what all that does is it simplifies the value from an exponential number or a number in scientific notation to a simple number that has a value between usually 0 and 14, or it could be higher for these. It could 15, 16, but it turns it into a much simpler number that's easier to understand and easier to compare. So Ka is 1.8 times 10 to the minus 5. I've just rounded off. I take the negative log base 10 of that, and I get out the pKa is 4.76. And so that's what I'm going to see in section 21 of the data booklet. So for ethanoic acid, 4.76 is its pKa. So the pKa is a different way of telling me how much does this acid dissociate. And over on the side, I've got it highlighted. pKa, like for any p-value, is negative log base 10 of Ka. If I want to undo pKa and figure out the Ka value is, it's the same way I would undo pH. I do 10 to the minus pKa. In this example, I would do 10 to the minus 4.76. I plug that into my calculator, and that will give me back the Ka value. So you can go back and forth between them. Okay? They both really represent the same thing. They represent how much do these things dissociate. Here's a little confusing part, though. With Ka, what I talked about on the previous page, I said, well, the bigger the Ka value, that implies more dissociation into ions and a stronger acid. Now, this worked the same way with pH. Okay, what I just said before is true, but so higher values of Ka implies a greater dissociation. But the way the math works, the higher the Ka value, the lower the pKa value. And I'll show you the example right here. So when Ka, if I compare these two things, the methanoic acid has a larger Ka value because it's got a less negative exponent. So just from looking at the Kas, I would know that methanoic acid is a stronger acid than ethanoic acid. It has a higher value of Ka. But when I plug both of these values into negative log base 10, the pKa actually comes out lower. Okay, so higher values of Ka imply greater acid strength, and lower values of pKa imply greater acid strength. So I know that's a bit confusing, but same with the H+. I think I mentioned this already, that anytime you're dealing with a p-value, lower implies stronger or implies greater. Anytime you are not dealing with a p-value, then higher implies greater. So that p-value, because it represents a negative exponent, smaller negative exponents are bigger values. And so that's why smaller p-values actually represent greater dissociation or greater strength. Okay, so it is confusing, but it is a concept that you will be expected to work with. Kb and pKb works exactly the same way. We are going to, have Kb values. The bigger they are, the stronger the base. For pKb values, the lower they are, the stronger the base. So methylamine is a stronger base than ammonia, both because it has a higher Kb value and also because it has a lower pKb value. So here's the table once again. Lots of examples that they can reference. They've given you their dissociation constants. So which of the above acids is the weakest? Well, if I have a p-value, then low means strong, so high means weak. The highest value that I see is this one, 2,2-dimethylpropanoic acid, which would have the largest acid dissociation constant. Largest Ka value is strongest, and that means lowest pKa. So question 2, for this one, the answer would be methanoic acid. Of the ones listed here, this has the lowest pKa, that would associate with the highest Ka. In which of the below amines is the strongest base? The one with the lowest pKb value. The lowest value that I see is this one, 3.16. Diethylamine is the strongest base in this list. All right, so how do we actually do the calculations? Well, we've got the Ka expression. Remember, it's very similar to an equilibrium constant expression. And so essentially, there's different types of calculations you're going to be presented with. Either you're going to use a pKa value from that table and a given acid concentration, and you'll solve for H+ and or pH. So you'll know this one, and you'll know pKa. And if you know pKa, you can get Ka. And once you know these two things, you can use ICE calculations to solve for these ones. You might also get pKa's and pH values. If you know the pH, you can get the H+. And if you know the pKa, you know the Ka. and therefore you'll know everything except the acid concentration. And finally, you can use, if you know an acid concentration and the pH, you could solve for an unknown Ka or pKa. So it all ends up being algebra, but there's sort of different approaches that you can get. With weak-based calculations, there's always the added step of you're really solving for OH minus and POH, and so remembering that POH and pH add up to 14 is the last step. So we'll look at one example as quickly as possible before wrapping up this video. They are basically ICE calculations with one major assumption that lets you make the calculations much, much simpler. So if we have a 0.1 molar ethanoic acid solution, how do we calculate the pH? Okay, we set up our ICE scenario to make sense of this. It's at equilibrium, and remember, we don't consider the water. It's not going to be part of our expression, so I'm just going to ignore it. So initially, I have 0.1 moles or 0.1 molar of ethanoic acid and 0 of each of these. It's a 1-to-1-to-1 ratio, so as it goes to equilibrium, I'm going to lose X from the weak acid. I'm going to gain X of both the ions on the other side. And so at equilibrium, the concentrations I'm dealing with are 0.1 minus X, X, and X. Okay, so now I come down here to my Ka expression, and I'm going to plug those values in. I plug in X for the two ions, and I plug in 0.1 minus X for the concentration of the weak acid. I also want to plug in the value of Ka. The way I do that is I go look up, here's the pKa value, 4.76, and the relationship to actually get the Ka is 10 to the minus pKa. So the Ka is 10 to the minus 4.76. I don't really have to simplify it yet. I don't have to plug it into my calculator yet, but this is how I get the Ka value. Okay, so I get the Ka value and I plug into my equilibrium constant expression, my Ka expression, and I can simplify it down to this: X squared on the top, 0.1 minus X on the bottom. Now, you may say, I thought we didn't have to do quadratics, and we don't, because we get to make this really wonderful assumption. And I'm going to show you that it works afterwards. For now, here's what we assume. We get to say that because X is so small, so little of this acid actually dissociates, 0.1 minus X is almost the same as just 0.1. And a lot of people look at that and say, well, then that's a load of garbage, and then the top should equal 0. Well, this is the assumption we're going to make. And again, I'm going to show you at the end that actually it gives us the same value. So if we simplify it down to this, we just approximate away this X here, because we say it's so tiny that it doesn't actually matter. I'm going to just use this equation to work from here. So I've got 10 to the minus 4.7 equals X squared over 0.1. Okay, so I get rid of the 0.1. I multiply both sides by 0.1, which is 10 to the minus 1. So that turns into 10 to the minus 5.6 equals X squared. So to solve for X, I take a square root of 10 to the minus 5.6, and I get my X value. Well, remember, X actually represents H plus. So by solving for X, I have solved for H plus. The H plus concentration is therefore 0.00132 moles per dm cubed. And if I want to know the pH, I take the negative log base 10 of that number, and I get a pH of 2.88. So just to compare, if we had had a strong acid that was 0.1 molar, we would have immediately assumed that its pH is 1, because 0.1 is 10 to the minus 1, and with full dissociation, the pH should be 1. Notice that for a weak acid like ethanoic acid, the pH is 2.88. That's almost 100 times weaker for H plus concentration than the same concentration of strong. So when we talk about the difference in dissociation, strong acids dissociate almost 100 times more than the weak acids that they compare to. Now, we've done this assumption, which is basically the concentration of the weak acid is about the same initially and at equilibrium, because there's such a little amount of dissociation. Now, some people don't like to believe that, so I have this don't believe me section. If I hadn't done that change here and I had just tried to solve this as a quadratic, eventually I would have gotten to this quadratic here. And then if I solve for the roots, the only root that makes any sense that's not negative is that X equals 0.00131 moles per dm cubed. And if I plug that into negative log base 10, I get a pH of 2.88. So is this assumption, 100% accurate? No. but at the precision levels that we are dealing with our number of significant figures, it will give us the same pH value every time. So the assumption that you get to make is that because the acid or base dissociates so little, the equilibrium concentration is actually equal to its initial concentration. So we don't actually do the X part. We just assume it away. We get rid of it, and we just, whatever we started out as, that is our equilibrium concentration for our weak acid and base. It makes the calculation steps a lot simpler, and it actually doesn't change our pH value at this level. So that's the process for calculating, doing a pH calculation. I told you these calculations could go in either direction, but you use pKa values to get Ka values. You simplify the expression using that assumption, and then you solve for X. X is the concentration of H+, which allows you to get pH. And we will do lots of practice with this. This is a very important type of calculation that shows up on basically every IB exam, and we should be really comfortable using it inside and out.